In it. And we're back with the Biochemical Kinetics Assignment. We gotta do this fast, powerful, on time, not on time, before time. We gotta complete this. So experiment 13, it's oxidation of thioether with hydrogen peroxide. We have to formulate the Baxter-Valent equation. What is the reactant? Reactant product, right? What's the reactant? Oxygen? I don't know. I don't know. The data lists DMSO as product and hydrogen peroxide. The data lists DMSO as product and hydrogen peroxide as oxidation byproduct and oxidation byproduct. Okay. With the HF 285, that's for oxidation byproduct. Okay. Which matches liquid H2O. I don't know if it's, I don't know liquid H2O as that number. Now, the natural balanced oxidation of thioether. Dimethyl sulfide CH3 twice S. Okay, that's a thioether. By hydrogen peroxide to give dimethyl sulfoxide. I never would have guessed. Okay, that's this DMSO. But not gonna lie, I never would have guessed this thing, DMSO. So the reactant is the compound labeled reactant in your table. The reactant is the compound labeled reactant in your table. In practice, that reactant is dimethyl sulfide. This one, right? Yeah. Yeah. Yeah, that's the one. That's the one. Ya feel me? Ya feel me, man? Now, delta G of oxidation at the standard conditions 298.15 Kelvin. Is it spontaneous? Is it though? I don't know. Step 1. Compute delta H product minus reactant. Reactant delta HF equals minus 65.3 kilojoules. S0, what's S0? 196.4 joules per Kelvin. Where my dog at? Where my headphones at? Where my headphones at, dog? My headphones. Okay. Got him. Fucking got him. Now, calculate the equilibrium constant for this reaction at standard condition. Uh-huh. Is the endowed reaction equilibrium on reactant or product side? Uh-huh. Determine the temperature at which oxidation is in equilibrium. The Gibbs free energy of the oxidation at standard condition is it spontaneous? Compute delta H, products minus reactant, yeah. Yeah. Compute delta S, yeah. Now delta G, yeah. From that, it's negative, so it's spontaneous. Okay. Now equilibrium. That's it. It's the reaction equilibrium on the reactant or product side. Which side is favored? What? Oh, okay. So the reaction spontaneously proceeding. Calculate the free enthalpy of the. Oh, that's C. Okay. D. Calculate the equilibrium constant. Equilibrium constant. Use log of K equals minus Gibbs free energy, change in Gibbs free energy by RT. RT, yeah. K. Oh. Oh, what have you done? This huge K means equilibrium lies overwhelmingly overwhelming overwhelmingly overwhelmingly on the product side. Overwhelmingly. Damn, some tough words, eh? Some tough fucking words. It's a command. Yeah. I'm so happy you're at home. Wait. Can do whatever. This is the third assignment. Oh, fourth. This is the fourth assignment I got for thermodynamics. And Okay, DeepSeek is having a little bit of confusion. Let it be on the background. Now, uh, I mean, I understand that one of these is a natural logarithm. The other one is I don't know, unnatural logarithm. I think this one's the natural logarithm. So converting normal log to natural logarithm takes a step, I guess. Huge K means equilibrium lies overwhelmingly on the product side, practically complete conversion under standard condition. Hmm. I need a little bit more explanation as I forgot what the equilibrium constant was actually meaning. And temperature where the oxidation is in equilibrium. Temperature where oxidation is equilibrium. I know this. No, I don't know this. Uh, set. Oh, you just used this equation. Oxidation equilibrium means delta G zero. Why? Why? I need interpretation extremely high, far above usual experimental temperature, so the oxidation is spontaneous. Overall practical temperatures. Okay, I need to know a little bit more. Short summary, one line answer. Second law, entropy of the universe. I know those. I know C. Now, my doubts arise from part D. What's the equilibrium constant? I forgot what the term stood for, and why was both type of logs involved here. Now for part E, what does it mean Gibbs free energy is zero when the oxidation is in equilibrium? Conceptually, oh, why do you blink, bro? Oh, the whole thing is, bro. Chill, bro. Still going? Okay. Conceptually, what do you mean study? Nah, I'm not. I could use it, but not right now. Conceptually, the equilibrium constant K tells us how far a reaction proceeds before reaching equilibrium. That is, the ratio of products to reactant at equilibrium under standard condition. For general reaction, the equilibrium constant is bleh. How far a reaction proceeds before reaching equilibrium. Equilibrium constant tells how far a reaction proceeds before reaching equilibrium. Okay, that is the ratio product. Okay. How K connects to Gibbs free energy. That's a direct thermodynamic link between Gibbs free energy and equilibrium. Gibbs free energy per mole, reaction gas constant, equilibrium constant. Why we use Ln, and the formula uses natural logarithm because, oh, that was a natural logarithm, okay. Because thermodynamics is defined in base E. Oh, that's one heck of a sentence. Thermodynamics is based on is defined in base E. What does that mean? I don't know. You just made me more confused. Are you happy now, ChatGPT? Now I am more confused. Stop. You feel me? You feel me, dog? But sometimes, for convenience or readability, people express the answers as log 10 to the base 10, especially when k is huge, like 10 raised to 39. The conversion is simple. It's simple. It's very simple. Okay, interpreting k. If k is very high than 1, products dominate. Reaction goes nearly to completion. If k is really low than 1, reactants dominate. Reaction hardly proceeds. K is approximately 1. It is in equilibrium, perfect equilibrium. In your case, oxidation completely forms products. Oxidation is in equilibrium. When a reaction reaches equilibrium, the driving force to move forward exactly cancels the driving force to move backwards. Energy wise, the system is perfectly balanced. You could say it's done moving downhill. When we say the oxidation is equilibrium, we mean the system's energy is minimized, the ratio of product is fixed. You mean fixed or equal? Overall composition doesn't change. This part I'm kind of confused. Why we solve for the temperature where this part just made me more confused on the whole thing because when you wrote E, I don't even know. I don't know what does that even mean. Like, I don't know what that number is or how that number is out. Or how that number is made up. So now, what's the next part? Okay, ratio is fixed. I get that. I get that. They don't change. Okay. Trying to find my way back. What is this mysterious E? E pronounced as E. E. It's a mathematical constant, just like pi. It's approximately. It's a rational number. The decimal never ends or repeats. Never repeats. What do you mean never repeat? Like there's two eights, there's twos, there's two ones. What do you mean? What do you mean, bro? It's the base of natural growth. These are big words, okay? Why is E important? It comes from studying things that grow or decay continuously, like bacteria growth, radioactive decay, interest in bank accounts, chemical reactions approaching equilibrium. All those follow a curve that is described by E. If 100 bacteria that double continuously, their growth rate is described by N equals N0 into E raised to KT. So E naturally shows up when we deal with continuous process. Why was E here? E, okay. That's what we call natural logarithm. Now, what's the difference between in thermodynamics and chemistry? Ln is used because reaction and energy changes behave continuously, not at the powers of 10. But for easier reading, like we say k equals 10 raised to 39, we sometimes convert ln to log 10. It's the same number, but just a different way of writing it, like converting kilometers to miles. Uh huh. Because the Boltzmann factor. Now there's a lot of shit. All equilibrium expressions come from exponential relations. This comes from probability and energy distributions that follow E equals E raised to minus E by RT, which again involves E. So E appears because nature behaves exponentially. Nature itself behaves exponentially. Molecules don't switch states in steps of 10. They do so continuously following this mathematical pattern. Simple analogy. Mhm. Okay, I mean, I kind of get it, but it's if I go deeper, I'm just gonna go keep on asking questions and nothing's gonna happen today. So no, I yield. I yield science. I yield. I. What was the second law of thermodynamics? For every spontaneous reaction or every reaction, the overall entropy of the universe increases. Something like that. Such a weird law. Not gonna lie. For any spontaneous process, the entropy of the universe increase. We gotta start right. We gotta start. We gotta start writing. Am I right? Oh, no battery. Really? Wheelie? Wee. How do I charge it? How do I charge it? Power bank. Power bank. I wrote a lot of shit for example 14, okay. Damn, example 14 is a big one. Is it example 14 or 15, the bigger one? I did not see the change to example 14. A. Okay, example 15. Okay. Okay. Okay, okay. Oh, example 15 was pretty small. Well, let's start. What is this? It's a biochemical kinetics idiot. No. Such a stupid little guy, stupid little guy. Biochemical kinetics and okay, biochemical kinetics. For and this would be example 14 or 13. No, fucking 13. How do you write 13 in Roman letters? X 1 2 3. Yeah. Second law. Second law of thermodynamics. What does it say? The second law of thermodynamics states that any spontaneous process, the entropy for any spontaneous process, the entropy of the universe just increased somehow. I don't fucking know. But entropy of universe equals entropy of system plus entropy of surroundings, giving value greater than 1. Yep. Let's do it. Why is it not sharing? Why? Okay. For any spontaneous process, the entropy of the universe always increases. Universe system. Stop plus surroundings greater than 0. And that's basically the first part, right? Yeah, that's basically it. I gotta can I do the second one just like that? Okay. Come on, bro. Come on. Come on. Where is it? Where is it? Yep, you got it. What's part B? How is it? Balance reaction equation. Data, data, whoa, 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 whoa. Okay. So balance equation, you for sure. CH3 twice, CH3 twice. H double bond O, H2O2, H2. Okay. What is this equation called? Named? Ah, thioester. Let's go. So the reactant. So what's the reactant? It's a dimethyl sulfide. Sulfide. No, I gotta do that question alone. Okay. Ah, God's sake. Just be right back. Part C. Reactant that would be this product. Okay. DMSO is the product. This would be DMSO. What's with the DeepSeek, bro? DeepSeek, how you doing? How are your answers? Yeah, same equation. 2, 2, 2. Is that correct, Mr. Kinda, yeah. I would say DeepSeek is a bit more precise. Damn, DeepSeek crushing those numbers, eh? Okay. I could just do this. Bish. Bish, what would you do? Oh, that's exactly what you did. Okay. Temperature at equilibrium. This is unrealistic physically. Unrealistic physically, but mathematically from the given data. How much adiabatic expansion? Whoa. What? Okay, we went to. Okay, we got 4,966 kelvins. It is correct. Oh. Can you see my eyes? Let me do something that you can. Now that's the full light, right? Ah. I could blind the camera by flashing it light. Okay. So, yeah, the numbers are correct, at least for the first one. So I know the C part. In this reaction proceeding, okay. Calculate the equilibrium constant for this reaction at standard conditions. Is the reaction equilibrium on the reactant or product side? Yeah. So it's D. Ooh. Good music. Okay. Natural logarithm of k or natural logarithm of equilibrium constant equals. Now, what is the name of this equation? DeepSeek, you got an answer? The name of this equation, do you have it? Bro, come on, bro. You don't have that shit? No, you did not name the equation. I told you to name me the equation. The It was Boltzmann or it used Boltzmann constant. What's the name of this equation? Gibbs-Helmholtz relation. Gibbs-Helmholtz relation. Okay. So natural logarithm of k equals minus delta Gibbs minus of Gibbs free energy by RT, right? Yeah. And the main thing you have to look on is the units. Fucking units, brother. Did you convert it? Nah, did not convert. Okay. Kilojoule per mole. RT is joule per mole Kelvin times Kelvin. So this one's is kilojoule per mole, and we have joule per mole. Okay, we converted to okay. Calculate the free enthalpy of free energy. Why would you use that type of words, brother? Brother. Kilojoule per mole. 196.4. H2O2, hydrogen peroxide. What do we got? 109.6. One 88.3. Oxidation byproduct as we bought it, right? Ooh. That's the song, bro. Do I have to write something else? Nope. So 'God damn, I forgot the temperature. This is C, bro. Yeah. 298. Okay. So this would be no, 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 no. 490, 490, 490 plus. Ah. Minus 47.9 joule per mole Kelvin. $251 point. Spontaneous process. What was part D? Is that the Boltzholzman? Yeah. What's the name of the equation? Calm down. Gibbs free energy and equilibrium constant. Oh Lord, I'm hungry, bro. What the fuck? Why am I hungry? I just ate. Not just, but still. Come on. Hungry. For real, though. Hungry. Okay. So, I forgot the units, bro. Uh, 8.314. Yeah, that's enough. Okay. $251.2. I did not do the calculation. What was it? 251.2. Oh. Okay. If I understand from this, right? Oh, well. Wait. Wait. I mean, I. Wait. Was that right? 251. Why is 222? No, it's plus, right? I don't understand how the values changed. 47. Yeah, 47.7. That's okay. To 36.9. Yeah. Let me do the math again. Okay. That's what I missed. Got the answer. I don't know if that makes a difference, but let's see. 90. Okay. That did made a difference. Okay. Okay, we got a number pretty close. Product side. What's the E part? Temperature when oxidation is equilibrium. Okay. Two 22.6. 47.9 into 10 raised to minus 3 kilojoules per 47. What? Okay. 4,647.2 Kelvin. That is too high. Too high temperature. Therefore, what was the reasoning? Extremely high, far above usual experimental temperatures. Oxidation is spontaneous. Overall practical temperature. Too high temperature. That's it. So that's one question. Was much easier compared to now that the other questions are harder. Well, that's it for today. YouTube, I have a Halloween party going on, so I'm just gonna go check it out because some of my friends are coming. Let me see what's going on. I'm not a big fan of parties, but if they call me, I should go, right? I should go. Peace out, YouTube.